Bismillahirrahmanirrahim. Assalamu alaikum. Hello students, welcome to the Electrical Engineering channel. In this lecture, I am going to demonstrate the derivation of electric field intensity uh, due to a point charge, but using Gauss's law. In the previous chapter, we derived this expression for electric field intensity due to line charge using Coulomb's law. But today I will use Gauss's law and I will show you that through both the methods we get the same result. So in this case, we are given this line charge and this line charge is distributed over the z-axis and the length of this line charge is assumed as L. So from this point up to this point, the length is L and this is rho from z-axis to the surface and the density of this line charge is equal to rho L. So the total charge is equal to d dot ds, right? And uh, this closed surface integration will be evaluated for this line charge, and this closed surface is established by this top surface, this bottom surface, and this side circular surface. This circular surface at the sides, this top surface and bottom surface. These three surfaces must be added together, and these three surfaces constitute the complete closed surface. So this integration will be evaluated for the side and this integration will also be evaluated for the top and bottom. Now since the charge is distributed over the z-axis, the electric flux density due to this charge will only have the rho component because it will be radially outward from the source, and this distribution won't cause any component of electric flux density either at the top surface or the bottom surface. So there will not be z component of this electric flux density and there will only be the rho component. So d is equal to d rho a rho, and for the top surface ds is equal to ds az, for the bottom surface ds is equal to minus ds az, and d dot ds for these two surfaces will have the a rho dot az, which is equal to 0. So we will have only rho component of the electric flux density. So this integration will be equal to 0 for top plus bottom surfaces because a rho dot az is equal to 0. For the sides, this integration is equal to dl d rho. So this is d rho, and the differential surface for the side is equal to rho d phi dz a rho, and a rho dot a rho is written over here, and this is d rho and this is ds. So phi varies from 0 to 2 pi, z varies from 0 to L, and a rho dot a rho is equal to 1. So it will become q equal to rho d rho into 2 pi L, and d rho can be written as q over 2 pi rho L, and d is equal to q over 2 pi rho L a rho because this is d rho, and we know that rho L is equal to q over L, so q will be equal to rho L into L. Rho L is the line charge density. So we can put Q equal to rho L into L. So L will be cancelled out with this L, and D will be equal to rho L over 2 pi rho A rho, and E is equal to rho L over 2 pi epsilon rho A rho. So this is the same expression for electric field intensity which we obtained using Coulomb's law in the previous chapter, and the same expression is evaluated using the Gauss's law. So Gauss's law is simpler, and this derivation didn't involve any complex integration or infinite integrations. So I prefer Gauss's law to solve line charge and point charge, electric field, and electric flux density problems. So that is all about our today's lecture. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.